到風力嘅壓力啦，然後利用個壓力都可以計算出你構件上邊嘅承載力。咁呢個程序上亦都係有一個 flowchart 喺入邊，喺 Figure 2.2入邊咧，你只需要按部就班一路按住程序走咧，你就可以計算到出嚟嘅。咁或者我哋再深入一啲講一講關於結構荷載方面嘅折算嘅方法同埋佢嘅分別喺2019同2004版。咁如果你睇到圖嘅左手邊就係一個簡化版嘅2004嘅流程，點樣去折算你嘅風力荷載、結構嘅荷載，而喺右手邊咧就係2019年版。咁喺兩本規範入邊咧都有第一樣嘢要計算嘅就係一個順向風向嘅風力計算啦。咁你睇到兩個粉紅色框住嘅位置就係佢兩個折算嘅方法啦。咁然後跟住喺2004版本身嚟講咧，其實都有需要去計算嘅所謂嘅橫向風同埋扭力嘅折算嘅，但係當日嘅規範咧就冇好詳細咁列出計算嘅方法，係需要你去參考一啲其他嘅相關嘅文獻。咁但係喺新版入邊咧，我哋就直接有一啲equations 啦，係可以直接計算出咗所謂嘅橫向風同埋扭力嘅承載力嘅。然後跟住喺舊規範入邊咧，你係需要計算所謂嘅diagonal wind 同埋本身 XY wind 嘅。咁喺新規範入邊咧就簡化咗，其實而某程度上我哋只需要計咗 XY wind 之後，利用 XY wind 利用呢個 load combination 咧去 combine 兩個 XY wind 咧就可以達到以前計呢個diagonal wind 或者係 along wind 嗰個XY wind 嗰個折算方法㗎啦。咁如果再睇落去，關於2004版以前計算呢個結構順風向嗰個折算嘅時候咧，以前係有兩個方法去做嘅，一個咧就叫 static approach， 另一個就 dynamic approach。咁依家2019年版咧，其實就簡化咗嘅，我哋只有一個 approach， 一個叫 unified approach。咁就算係 static 或者 dynamic 咧，都可以用呢個 equation 去計算嘅。咁如果你睇到呢個表啦，呢個表入邊好反映咗幾樣嘢。第一就係以前2004版喺圖嘅左手邊，就係佢以前你點樣去計算 along wind load 嗰個數值啦。而喺2019版入邊嚟講咧，其實計算嗰個程序同2004版基本上係相類似嘅。而新增咗個部分咧，就係依家喺綠色個框綠色嘅部分咧，就係喺2019年版入邊新增加嘅部分嚟嘅。而同時間咧，喺計算design wind reference pressure 啦、force coefficient 啦同埋 size dynamic factor 呢方面咧，係有一個升版喺入邊。咁一陣間喺後邊幾張 slide 入邊咧，我哋會逐一咁介紹嘅。咁係啦，咁我哋先講就係 directionality 啦。directionality 嚟講咧，如果同業有經常接觸到關於例如用風洞試驗去設計嘅時候，都會發現到其實喺香港喺唔同嘅風向吹嘅時候咧，係有一啲相應嘅節減嘅。咁喺規範入邊，我哋將佢規範化咗，咁變咗咧，如果呢一個 building 喺唔同個 orientation 唔同嘅時候，可以根據佢嘅坐向嚟 apply 呢一個 coefficient 嘅。咁相對嚟講喺西北方向嚟咧，個風向係可以節減得最多嘅，就喺呢個西北方向啦。而最大風向嘅地方咧，就喺呢個東北同埋北邊方向嚟，就係東南方向嚟咧，係比較上咧係會係大嘅。咁但係呢個都好容易就可以 apply 得到噶啦。而同時間，如果呢個標坐向唔係完全正北啊、正南咁咧，你可以用 interpolation 嘅方法咧去計算相關嗰個數值嘅。咁咧，跟住呢張 slide 咧，我哋就可以睇到關於呢個 sheltering 嘅 effects， 呢個亦都係一個新嘅 feature 嚟嘅。咁喺圖嘅右手邊嘅一個wind reference pressure 咧，其實同2004版相對嚟講係冇改變嘅，係絕對係 exactly 一樣嘅。咁喺以前2004版入邊咧，就等於 case one 啦，因為以前係冇 sheltering 個考慮嘅。咁例如一個 building 係200米嘅，我哋想知道佢150米嘅時候嗰個 reference pressure 咧，咁你直接喺個表度就可以度到出嚟㗎啦。咁但係如果我哋 apply 咗sheltering 嘅時候，我哋係可以計算一個節減嘅高度節減嘅係數。當你計算咗個高度節減係數之後咧，相對嚟講，你個 風壓嚟講咧，係可以相應咁減低嘅。所以，但係實際嘅程序咧，我喺下一步喺我同事咧會喺 Part 2入邊咧會詳細咁再解釋俾你點樣操作。咁另一個 update 啦，頭先講啦，就係關於呢個關於其中裏邊每一個以前嘅 design wind pressure 啦、force coefficient 啦同埋 size dynamic factor 本身入邊嘅修改。但係 for design wind reference pressure 頭先都講咗，其實本身個 pressure 本身咧係冇修改嘅，只不過因為加多咗 directionality 啊、shelter 喺入邊咧，所以佢又相應嚟講都係有咗一個升版嘅。咁喺依家見到嗰張 slide 入邊咧，大家見到就係以前2004版，大家點樣去計算個 force coefficient 啦，係 based on table D1 同埋 D2 啦。咁新嘅咧2019版咧，我哋就用咗一個 graphical 嘅代表，咁只需要你計算咗個 B over D ratio 啦，或者同時計埋個 HE over D 呢個 ratio 嘅時候，你就可以直接喺個表度揾到你相對需要嗰個數值啦。但係同時間因為方便大家嘅計算啦，依家嘅年代大家都用電腦去做嘅時候，所以我哋直接就將一條 equation 係放咗喺個規範入邊，只需要你按照呢條 equation 計算嘅話，你都可以得到相同嘅答案嘅。咁另外一樣嘢有個 feature 喺入邊係舊規範嚟講咧，呢一個 feature 咧，其實就需要你哋去按照一啲literature 啊 special literature 去揾嘅。咁但係我哋依家相對嚟講就將呢啲 feature 咧都放埋落去個規範入邊啦。比如上一個 building 喺佢哋嘅corner 上面，佢有 round corner 啦，或者有個 cut corner 咁咧，其實呢個 effect 咧對風嚟講係有一定嘅折減，所以我哋將呢個折減係數亦都放咗落去規範入邊。而以前喺舊嘅規範入邊都有另一個問題出現，就係有啲 building 係相對係 regular 嘅 irregular shape。咁大家對於 determine 佢個 B 同 D 呢兩個 ratio 嘅時候咧，都會有一啲不同嘅考慮，亦都有不同嘅意見。咁所以咧，我哋喺呢方面咧，就直接將一啲比較上我哋叫做規矩啲嘅 irregular shape 咧，都放埋喺規範入邊，可以俾大家有個參考，就知道點樣去計算個 BD 呢個 ratio。咁用呢個 ratio 嘅話，你就可以用翻前邊嗰條 equation 咧，直接就計算出嗰個factor 出嚟啦。咁喺舊規範同新規範咧，都有呢個 dynamic factor for along wind 嘅。咁你都睇到啦，喺圖嘅左手邊就係以前舊嘅 equation 啦。咁大約有8條左右啦，1、2、3、4、5、6、7條。咁喺新嘅規範嚟講，我哋就將佢簡化咗少少，就變咗3條 equation。咁亦都係話可以直接就可以利用呢個 special 啦，就可以計算得到呢個 dynamic factor。好啦。咁之前都講咗啦，其中有一個喺舊規範入邊冇好明確嘅equation 或者係一個程序去做嘅，就係一個 crosswind 嘅 assessment。當一個 building subject to 一個 significant 嘅 dynamic response 嘅時候咧，你係需要去揾一啲相關嘅 special literature 去做一個 reference， 或者要去做 internal test。咁依家喺新嘅規範入邊咧，就有個比較簡單嘅程序，尤其是喺 torsional wind 啦。torsional load 啦，你只需要按照 cross 2.2.2咧嘅 equation咧，你就可以計算得到出嚟噶啦。而喺 along wind 方面咧，就有 equation 2 hyphen 2。咁喺下一張 slide 度面，我哋可以見到嗰條 equation 係點樣嘅。咁呢條就係equation 2 hyphen 2，就係用嚟計算個 crosswind 噶啦。而同時間咧，喺 cross 2.2.2咧，亦都有一個簡單嘅方法去計算一個 torsional moment， 只需要按照 eccentricity 同埋一個順向風或者橫向風嘅 loading， 咁只計算咗個 envelope case 出嚟，攞取大個 value 嚟用就得噶啦。好啦，關於 load combination 啦，喺 load combination 方面咧，咁之前舊規範就好簡單啦，都係話你要計4項等於 x、y 跟住 u_v，which is diagonal wind。咁但係喺新嘅規範嚟講咧，反而應該就最簡單咗，因為當你計咗所謂嘅 x、y wind 嘅時候，你只需要用個 load combination 嚟做咧，你就可以將佢加起上嚟，就係1加 0.0。1加 0.5， 然後再加 torsion factor 0.5 torsion， 咁如此類推啦，有三個 load combination 嚟要考慮啦。OK，之前都講咗啦，喺 喺呢個舊規範同新規範都好啦，都有一個 requirement 就係究竟個規範本身適唔適合你個 building，需唔需要考慮一特別嘅情況啦。如果你超出咗規範嘅用途嘅時候，你就會需要走去做 internal test 啦。但係喺呢個新規範入邊咧，如果你個 building 嘅 crosswind effect 係 significant 嘅話咧，當個 crosswind係大過個 along wind by 1.5倍嘅時候，呢個亦都係需要進行呢個 internal test 嘅驗算嚟再證明，因為個規範本身係有一啲嘅 limitation 入邊嘅 equation 咧，喺一啲超高層上面或者一個超 slender 嘅 building 上面咧，係唔係太合適嘅。咁第一個頭先我哋之前嘅啲 slide 都已經 show 咗啦，就係點樣去計算個 along wind 啦，同埋利用 equation 2-2就可以計算 from 一個 crosswind 嘅 moment 出嚟。當你將兩個 equation 兩個 value 相比嘅時候，如果係大於 1.5 嘅話，就需要去做 wind tunnel 啦。頭先再 repeat 咗頭先講過嘢啦。咁其實呢一個某程度上係一個相應翻喺2004版入邊7.6個 clause 一樣啦，就係當你個 crosswind 係 significant 嘅時候，當超出咗規範能夠容許嘅程度下，你就可能就需要去做用 internal test 去 verify 翻你個 wind load。咁另外頭先講咗亦都有個新嘅 feature 就係關於舒適度啦。喺以前嚟講，就舒適度嘅 assessment 咧，就需要你係做 internal test， 然後先至可以 assess 得到嘅。咁但係依家有咗呢條新嘅 equation 喺入邊咧，你哋就可以直接可以計算到出嚟。但係同樣有個 limitation 就係頭先我講，如果你個 crosswind effect 太大嘅話，呢個 equation 都可能唔適用嘅。咁同時間咧，喺比起舊嘅規範嘅做法咧，依家有一個新嘅 acceptable criteria。呢個 acceptable criteria 咧，相對嚟講係一個 frequency dependent 嘅，即係話你個 building 係一個唔同嘅 frequency 下面咧，你個 acceptable criteria 咧係會 varies 嘅。咁係即係一個更加精準嘅方法去折算你個舒適度同埋一個 comparison 嘅。咁喺規範入邊咧，你下嗰幾張 slide 咧就有一啲比較上係side tracks 比較上 minor 啲嘅 features 喺入邊 ，which 我哋都放埋去規範入邊嘅，比如 temporary structure 啦。temporary structure 嘅 window 大家都知道，喺舊嘅 PINAP 啊入邊都係用緊，可以話用多70嘅。咁例如計算呢個 hoarding 啊，一啲 non-residential 嘅 temporary structure，例如 bamboo shed 啊，咁咧就可以用到37% of 嗰個 wind pressure。咁呢件事以前咧喺 PINAP 入邊嘅，咁我哋亦都將佢規範化咗，將佢放埋落去個規範入邊，咁就變咗大家可以唔需要再去抄 PINAP 啦，直接就喺規範入邊可以引用到呢啲嘅 benefit 啦。咁另外一樣 feature 係喺個規範入邊反映嘅，亦都增加咗喺入邊嘅，就係喺舊嘅2004版入邊咧，就話steel structure 同埋 concrete structure 咧，只係俾咗一個數值 for 呢個 damping 嘅。咁但係佢有條尾喺度嘅，有少少就係話，如果你個 building 咧係好 slender 嘅時候，或者係一個 stocky 嘅 building 嘅時候咧，其實呢個 value 咧，你係需要再 assess 嘅。咁亦都係需要你哋揾一啲 special 嘅 literature 特別嘅相關嘅文獻嚟參考嘅。咁但係亦都因為咁咧，所以我哋就直接俾咗一個 reference，就係將比較 stocky 嘅 building 咧，例如細過4嘅，咁佢嘅damping ratio 係一個咩 range 咧？咁我哋都喺今次喺個新規範入邊就升咗版，將呢個數字都放咗落去啦。咁同時間亦都將計算 structural loading 同埋計算舒適度兩方面喺最新嘅 research 入邊反映到佢哋嘅分別咧，亦都喺呢個新嘅規範入邊咧，其實係反映咗噶啦。咁另外喺呢一張 slide 入邊見到啦，就係喺香港亦都有好多情況出現，就係一啲叫做我哋叫做大底盤多塔樓嘅情況，而喺舊嘅規範嚟講咧，大部分只係apply for 一個 single tower 啦。咁我哋依家喺新嘅規範入邊咧，我哋就嘗試去俾一啲 guideline 出嚟，去點樣操作，能夠將呢啲咁嘅情況咧，都可以係折算得到嘅。咁但係因為呢個暫時都係喺一個 research 嘅階段啦，我哋揾到嘅文獻唔係好多，所以將呢個 guideline 咧就放咗喺呢個 expenditure note 入邊作為一個參考嘅。咁大家就可以利用呢個參考，可以睇下點樣去運用啦。咁佢呢個張 slide 就 show 到個 along wind 嘅 case 啦，就係 sorry 唔係 learning 係 translation 嘅 window case 啦，而後邊呢一張咧就係一個 assessment for 個 torsional case 嘅。咁喺個 EN 入邊有個比較詳細嘅解釋嘅，咁大家可以 refer 到嗰度去參考一下。咁第二部分喺第一 part 嘅第二部分咧，就係關於立面所謂 cladding 嘅何在。喺新版入邊，其中一個最大嘅升版嘅 reference 咧，就係以前舊版2004入邊計算個風壓嘅時候咧，係根據個佢嘅 reference height 嚟計算嘅。咁但係喺依家新版入邊咧，嗰個 pressure 個 reference 咧就只係剔咗。應該話相應嚟講就係剔咗喺個 reference height 上邊。呢個咧其實咧就係喺咁多年大家好有機會參與到 internal test 嘅人咧，發現到呢個係一個常態嚟嘅，亦都係一個比較合理嘅 latest research。所以我哋就將佢常規化放翻落去規範入邊。而呢個 adopted approach 咧，其實咧喺世界上面好多規範啊，例如 ASCE 啊、BSCN 啊，都係用同一個 reference 嘅其實。咁喺規範入邊亦都cladding 呢部分咧，亦新增咗一個叫做 size factor， 就係話如果你個 panel 嘅大小咧係會影響到你承受個風壓嘅 probability 嘅，而亦就可以利用呢個表咧，相應翻你哋見你哋嗰個 building 個 panel size 咧，就可以 work out 一個可能係一個 reduction， 亦都可能係一個好等於好似 H factor 一樣咧，係會增加嘅 factor 嚟嘅，係相應翻咁多年嘅喺 Wintunnel 入邊嘅 research 反映翻出嚟嘅情況嚟嘅。其實咁佢就分咗3類嘅，一個就 corner zone 啦，一個就 edge zone 啦，然後剩翻嚟嘅地方就叫做 others。咁其實大家都知道啦，通常喺個 edge 同埋個 corner 嘅地方咧，個 wind pressure 都會大啲嘅。咁呢個其實已經反映咗出喺嗰條 curve 上邊㗎啦。咁同時間喺 cladding 呢一個部分咧，我哋就增加咗一啲比較細節上嘅嘢，就係例如一啲細嘅 architectural feature 啊，咁我哋都有一啲相應嘅 force coefficient 擺咗落去，咁係增加咗，就變咗可以希望同業方面就簡化大家同業去揾一啲相關嘅literature去計算嘅。同時間例如一啲 freestanding wall 啊，好似 hoarding 啊方面，我哋都補充咗一啲 coefficient 喺入邊嘅。有一啲喺同業方面即係我哋喺咁多年操作上面咧，都發現到有個問題，就係有時好難去 define 啊，就 edge zone，因為喺圖表上面好難，通常只係解釋一個 edge zone 喺個 wording 上面，就冇一個好仔細嘅或者係相對個exactly 個 location 或者個 definition。所以今次我哋喺新嘅區份入邊，同埋喺 EN 個 explanation note 入邊咧，我哋就增加咗個 section 落去解釋，你 apply 個 edge zone 係嗰度有幾喺邊個範圍入邊咧，我哋叫 edge zone 咧，由邊個風向嚟嘅時候，邊一個 direction 先至係 edge zone 咧，咁我哋係增加咗呢個篇幅喺入邊嘅。好啦。咁另外第3部分啦，就關於 wind tunnel test 啦。喺舊嘅規範入邊咧，係冇提到呢一個部分嘅。咁喺呢個新規範咧，我哋就增加咗一個 section 喺裏邊，就將做 wind tunnel test 所需要嘅quantitative guidance 啦，係例如 topographic 嘅大小啦，個 model 嘅大小啦 ，proximity model 嘅大小啦，同埋一啲關於做 testing 嘅時候所需要個 sheltering obstruction 嘅 removal 個做法啦，都喺新嘅規範入邊咧，都增加咗呢個篇幅，等大家有一個 guideline 可以去 follow。而同時間有一個有啲關於我當然做完 internal test 之後，究竟我哋要取個 value 個 lower bound 係幾多咧？咁亦都喺呢個區範入邊咧，我都有再增加咗個篇幅落去解釋嘅。咁簡單啲咁講啦，喺舊規範嚟講，2004版，當你係好 unusual 嘅 shape，有 special 嘅 topographic surrounding 嘅時候咧 ，oops 得咗，係 sorry 啊，跳咗出嚟嘅，唔好意思啊，啱唔啱啊？有啲嘢跳咗。唔好意思啊，跳咗出嚟喎， 係咪再 share 過？呢個得唔得？得唔得？我 share 咗咯，唔係冇咗，唔見咗個乜嘢 team，縮咗呢個先。呢個再嚟個得唔得？呢個係得唔得？唔好意思，有少少技術上嘅問題。頭先講到啦，喺2004版入邊咧，如果你嘅 building 或者你嘅 surrounding topographic 係比較上 unusual 或者 complicated 嘅時候咧，你哋就會進行一個 wind tunnel test。而喺 wind tunnel test 入邊咧，出嚟嘅 result 有3個 configuration 啦。第一個就係 existing condition 嘅 wind tunnel 個 building 同埋個 surrounding 係 existing 嘅 condition 啦，或者有一個就係 removal condition， 就係將周邊嘅 building 逐一咁 remove 咗佢，然後考慮佢對佢嘅影響啦，同埋就係一個 envelope case of 唔可以少於0.7 of 個曲嘅 along wind，right？ 咁呢個就係舊規範入邊嘅要求，或者係舊規範個喺2004版入邊個 practice 嚟嘅。咁喺2019年版入邊咧，如果第一你係超出咗，好似頭先講啦，你大概200米，或者又係同樣有頭先嗰兩個 condition 咧，係一個比較上 unusual 嘅 shape， 或者有 complicated 嘅 topographic 嘅情況下，咁你去進行呢個 wind tunnel， 或者係頭先話喺規範入邊，你計完之後個 crosswind effect 比起嗰個 along wind 嘅 effect 大於1.5倍嘅時候，你都會進行一個 wind tunnel test。但喺 wind tunnel test 上邊咧，就有一個情況就可以可以有兩個情況啦，就係頭先翻轉頭去第一個情況就係話已經一開始你就已經係超過咗200米啦，同埋有嗰啲 unusual 嘅情況啦。咁你做 testing 嘅時候咧，個 maximum value of 你個 wind tunnel result 咧，你係可以係一個 envelope case of 個 existing 嘅 configuration， 然後咧喺 removal case 嘅時候咧，你係可以打個8折，或者係7折 of 一個曲嘅 along wind 嘅 envelope case。所以比起以前舊版嚟講咧，2004版嚟咧，其實咧做完 wind tunnel test 之後嘅 result 咧係相對咧係優化咗嘅，可以。但係如果你唔做嗰個 removal case 嘅時候咧，淨係有 wind existing 嘅 condition 嘅 case， 同埋個 compare 個曲嘅時候咧，你要取個 value 個 envelope 咧，就要需要打個8折啦，就唔可以好似前面嗰個 case 係做個7折嘅 case 啦。咁但係相對嚟講，你做少一個 configuration 咯。仲有一個比較重要嘅 point 要邊嘅就係，如果你 follow 2019年版嘅程序去做呢個 wind tunnel 嘅話咧，咁你按照咗個 position 去做嘅時候，咁就變咗唔需要好似以前咁係需要去經過 test set，唔需要再 require 個 SEC meeting， 直接就係可以係擺落去個 submission 入邊用。好，立天交俾你啦。我同事立天會往下解釋關於呢個利用呢個 work example 嚟解釋一下點樣操作呢個新嘅風嘅規範。
好，Thank you, Alexis. This is Neptune. So following what is described by Alexis, I'm going to show some working examples to introduce the detailed calculation procedure. Within this part, there will be 3 contents. The first one is a general briefing about the sheltering effect calculation. And the second one is an actual working example. This working example is 90 meters tall L-shaped building. And the second work case will be a taller building, so that is about 190, and it's a rectangular shape, also with some corner modification. So we go through the three contents one by one. The first one is the general rule on sheltering effect calculation. Alexis has introduced, so it's a new feature in the 2019 code. Within that, if we consider the sheltering effect, we can get some benefit. So we want to touch into more details because this is quite new. It hasn't appeared in the previous code. So the sheltering effect is something, for example, as explained in the first part, if the elevation is 150 meters, so we assess the wind pressure. That is for example, in the 2004 wind code. But now, if due to the sheltering effect, physically it's something like the wind profile is lift upward. So for example, if we say the displacement height is 50 meters, so then previously we assessed the wind pressure at 150. Now, still for the 150 meters tall, we only need to calculate the wind pressure at 100 meters. So that's the real benefit due to sheltering. So by adopting the sheltering effect, our wind pressure will be reduced from originally 3.05 kilopascal at 150, now to 2.686 at 100. So this is how the sheltering effect will help us. So the key point is how we can calculate the displacement height. The calculation of the displacement height is given in the Appendix A2 in the Code of Practice. So actually, it is controlled by three parameters. So here we can see within the formula, we can see the HI. HI is a particular objecting building height. So those are objecting buildings. So HI represents their building height. So you can see the displacement height will be bigger if the objecting building are taller. So the second one is related to the distance from the obstructing building to the target building. So that is XI. So you can see the further a building is located to the target building, the smaller the sheltering effect. So it all makes sense. And the third one is a lower cutoff limit. So this is to make sure that we don't have excessive benefit from the sheltering effect. So next are some general rules. So the rule number one is if we have only one obstructing building, we shouldn't take the benefit from the sheltering effect. The reason is the sheltering effect is something that we rely on other buildings to provide sheltering to reduce the wind pressure. So we need to avoid the condition that in a certain period within the design life of our target building, then this building may be removed. So that's why if we have only one objecting building, we shouldn't take any benefit. And the rule number two is if we have more than one objecting building, so what we need to do is we need to evaluate the exact sheltering benefit from each individual building. So how to do the evaluation? We need to follow the three formulas. But to make the code more user-friendly, we also provide a counter plot. This is in A2.3 in the Appendix A2. So this is exactly the same as the three formulas. So then based on this, we can identify the actual sheltering effect for each individual building. For example, the taller one, if we assume it provides the biggest sheltering, so we shouldn't take that into account. We ignore that. And then we keep searching for the second most benefit. So that will be this slightly shorter building, but closer to the site. And then we can take this into account. So the reason why we can take this into account is, so for two individual developments, so the chance of simultaneous redevelopment and the simultaneous removal of two buildings together, the probability is much smaller. So that's why it is allowed to take the benefit of the second. However, there's also a further rule supplemented in the explanatory note. It says if the two buildings, they belong into the same building lot, so they should be treated as a whole. So that means the two buildings, if they belong to the same building lot, so as a highlight in the black dash box, so they should be removed together. So the reason is within the same building lot, so the chance they are redeveloped simultaneously is much bigger. So that's why we have such a rule. So another case is, so we talk about the condition in the flat ground or flat terrain. But in Hong Kong, actually, we have many locations is in a slope terrain. So how we should treat it? So first of all, we should keep a clear idea is the topographic calculation and the topographic effect and the sheltering effect, they should be calculated separately. So then the topographic effect will be can be calculated independently. After that, so for the sheltering effect, we can see if wind blow from left-hand side, for example, that is from the bottom to the top. So it can be an attached flow, so through the slope of the mountain, but it can be also something like a direct purely horizontally. If it blows purely horizontally, we can see the actual sheltering from each individual building. So their effective sheltering height, so that can be highlighted in blue, are smaller than their actual building height. So that means if we take the actual building height as HI, the red one, that will be on the unconservative side. So what we should do is the code saying, in this case, we need to calculate the new objecting height starting from the base of the target building. So that's the blue height. So that is on the slightly conservative side. And in the opposite position, if the building is located at the bottom of the hill, and then the wind blow from the top to the bottom. In this case, also two scenarios. So attached flow, it will be the same as the original building height. But if it's purely blow horizontally from the top to the bottom, so the actual sheltering effect will be bigger than the actual objecting building height. So for this, because the codified approach is very difficult to accurately distinguish when will be attached flow, when will be purely blow horizontally. So we take it as a slightly conservative perspective. So we treat this case, we use the actual building height as the objecting building. Okay, so that's the slope terrain condition. And all the previous discussion, we consider it's a one-dimensional problem. But in the actual condition in a site, it's a two-dimensional, it's a plane. So then the code says for the sheltering effect, we need to evaluate for 4 orthogonal directions. So the 4 orthogonal direction, each direction covers about plus and minus 45 degrees. So that is a 90-degree sector. And if the building height varies across this 90-degree sector, so we should calculate the sheltering effect for each individual building, then do a weighted average. And according to our experience, in the code, it also says it allows the user to do an equal division. For example, within the 90-degree, we can equally divide the sector into smaller subdivisions, but the total number of subdivisions shouldn't be fewer than 4 divisions. And according to our experience, normally if we divide this into more divisions, it will lead a relatively easier calculation. The reason is you can see from the map, if we divide into small divisions, it's more easily for a building to occupy the whole sector. So that will that will simplify the calculation because we don't need to do the weighted average. So that's a brief introduction about the sheltering calculation principle. So now we go to the actual working example. The first working example is an L-shaped building. So this is the map where it is located. It is located in a relatively very dense urban center, and it's not very tall. The total building height is 90 meters. On plan, it is L-shaped building. The breadth is about 40 meters, and the depth on the two sides is about 15 and 25. And because the building is shorter than 90 meters, shorter than 100 meters. So the natural frequency we can use 46/h. So that is allowed by the code. So what we want to demonstrate through this working example is, so first of all, we want to demonstrate what the general workflow to conduct a codified calculation. So the general workflow will be at the very beginning, as Alexis introduced. So we make an initial assessment whether the standard approach applies or not. If it applies, so we move forward to do the along wind calculation. In the along wind calculation, we need, so the first of all is the ref design wind pressure that related to the directionality, sheltering effect, and the topographic factor. Then force coefficient, size, and dynamic factor. Then we can calculate the along wind force. Based on the along wind force and the geometry, so the B over D ratio, we can calculate the torsional load. Then we also need to check whether the building is a crosswind significant. So then we need to see if not significant, what we should do, and if it is significant, what we should do. And finally, is the load combination. And some bright points or key feature with this particular working example is, so first of all, the crosswind is not significant. So then later we will show another example that the crosswind is actually significant. Another one is we want to use this working example to show the procedure how to calculate the effective height and using a simplified approach. So then we go to the details to the step-by-step calculation procedure. At the very beginning, we need to have an initial judgment within this diamond box. So within this, we need to see whether the building is shorter than 200. Yes, and it is Euro shape, and then it is not located in a complicated surrounding of very complex topography. So pass all the through checking criteria. So then we don't need to go to the wind tunnel test. A standard approach applies. The next step, we calculate the design wind pressure. For the design wind pressure, the first step is a directionality. So we need to align our building. So this red box is our building alignment. Then we identify the 4 orthogonal directions. So that's the 4 orthogonal directions. Then starting from the 4 orthogonal directions, so we have starting from the 4 corners, we can identify the 4 different sectors, each cover 90 degrees. So here we want to show that although we start from the 4 corners, but actually we start the 4 corners, then draw a radar plot for the directionality starting from here will be the same as we draw the 4 directions from the center, then draw a radar plot here. So this will make it more convenient. So we start from the center of the building and then draw the radar plot. So the table A 1.1 will give the directionality for all the 8 key directions. So then anything in between we do interpolation. So that will be the radar plot. Then we use one sector, one of the 4 orthogonal directions as an example. If wind blows from the right to the left direction, so that will be Wx1 minus. So you can see it covers the northeast, that will be 0.84, the east will be 0.85, and the southeast, that will be 0.85. So we pick up the maximum among the 3, the directionality factor will be 0.85. So that's the directionality factor for Wx1 minus. So then we do the sheltering effect assessment. So we use a simplified approach because the building is located according to the EN, as say in Appendix A 1.2. There's a detailed discussion to say if the building is located in a very dense urban center, the surrounded building are of similar height of our target building. We can use a simplified approach to assess the effective height of sheltering effect. That will significantly reduce the complexity of the calculation procedure. So here are some general steps what we should do. First of all, we consider a range. The range is normally recommended as the smaller one between 500 meters and 6 times of the building height, the target building height. So the 500 meters is not a hard number. So if you want to go to 600, that's also fine. If you go to 300, it's also fine. It's not a hard number. But the general principle is the bigger the circle you draw, possibly the bigger the sheltering benefit you can take. However, if the distance is taller than 6 times of our target building, there'll be no benefit at all. So the recommendation is never to go beyond 6 times of the height of our target building. So that's the first step. The second step is based on the building alignment. So we need to identify the 4 key orthogonal directions. So each cover 90 degrees. Then a further step is within the 90-degree sectors, we can further divide into small subdivisions. As mentioned before, it can be divided equally. And if we have a higher resolution to have a small degree intervals, the calculation may be easier. So because of this, for this particular working example, we use 10-degree interval. So equally divided into 9 divisions. So next one is in the radial direction. So we mark several marks. So that is about with the radial distance increment as a 0.5h. So later we will show that this is for easier reference. And then we introduce some general principle how we can use the simplified approach to make our calculation easier. So the first one we need to bear in mind is within the 2 times of the target building height. So this is the distance. If the objecting building, they are within the height, which is 2 times of the target building. So then if we look at this counter plot, that means this one. So this is the horizontal distance. If this is within 2 times of our target building, as long as the objecting building, they are taller than 90% of our target building. So you can see the sheltering benefit is bigger than 0.7. So the horizontal is the distance, how far the objecting building to our target building. The vertical is how tall the objecting building relatively to our target building. And those counter plot is the sheltering benefit. So the bigger the number, the better. And the maximum we can take is about 0.75. So if we look at about this 0.7, it has been nearly the full sheltering. So we say within the distance of 2 times of the target building height, as long as objecting building heights are taller than 90% of our target building, so they can provide nearly the full sheltering. So if we look at in details of those objecting building, so they are all bigger than 80 meters. Our target building is 90, so 90% of 90 is about 81. So then we can say all those high buildings shaded in red, they can provide the full sheltering. So this is quite easy. So just by a glance, we can identify. And then later, we say if we consider a distance further beyond 2 times to 2.5 times, we can see here. So any building which are taller than 100%, any objecting building which are taller than 100% of our target building, again, they can give full sheltering. And even though some buildings which are not 100% taller, it's not of the same height, but of the 90% of the target building height, still we can get about 0.6 on the sheltering effect. So those are the buildings highlighted in green. So for those green shaded building, we can also get a relatively big sheltering effect, that is 0.6. So then we need to go to the detailed calculation. So according to the rule, we need to identify the first and the second benefit. So actually within the 2 times of the building, all those buildings, they can provide the full sheltering. So what we need to do is we just need to pick up the first layer as the most sheltering building. So that is from tower 1 to tower 5. Then we remove them, we ignore their contribution. So further to that, we pick up tower 6 to tower 8 to provide the sheltering for division 1 to 3. They provide the full sheltering. That is a 0.7. And then for the division number 6, we pick up tower 9 and tower 10. They also give the full sheltering. Further to that, for division 4, 5, and 7, we pick up tower 11 to 14. So that gave sheltering about 0.6. And then for the remaining one, division number 8 and 9, conservatively, we ignore their benefit. So that's 0. Then finally, we have known the sheltering benefit for all the divisions. So we just simply multiply the full sheltering 1, 2, 3, and number 6. So multiply by 4. And 0.6 sheltering, that is for 4, 5, 7. So multiply by 3. And this is 0. Then divided by 9. We can calculate very quickly, just maybe in 10 or 15 minutes. So we calculate the sheltering effect for this sector. And then we repeat the same procedure. We can calculate the sheltering effect for all the 4 divisions. So then the sheltering effect calculation is completed. So after the calculation of the sheltering effect, we can calculate and also together with the directionality, so we can calculate the reference wind pressure. So here, we also want to highlight is that we have calculated displacement height. The ratio is 0.51, and the total building height is 90. So the HD is a 45.9. So then, for the EZ, which are bigger than 61 meters, so those values, actually we can use equivalent effective height ZE equal to EZ minus HD directly. So those will be those values. However, we also need to bear in mind, if below this value, if we further still use EZ over HD, so that will give a smaller or even negative numbers. So then within the code, in appendix A2, there are equations A2 for A and A2 for B. A2 for B, it says if the Z is smaller than 1.33 times the displacement height, we need to use 0.25 EZ. So that is highlighted in the blue box. And then, because it is located in a flat terrain, the topographic factor is 1. So totally, with the QZ flat, directionality, and topographic factor, so all multiplied together, we can calculate the reference wind pressure. Next, within the calculation of a long wind force, we calculate the reference wind pressure. So we need to go to the force coefficient calculation. For the force coefficient calculation, I think I want to highlight another thing. So we have seen the benefit of sheltering effect that can reduce the reference wind pressure. Another benefit of the sheltering effect is actually, if we look more carefully for the force coefficient formula, so actually the H over D, so it is effective building height. So that means if we have a sheltering effect, the effective building height is also reduced. So if we look at the curve, it is very clear. The bigger the slenderness ratio, so that is H over D, the bigger the force coefficient. So if we have a sheltering effect, actually, we can also get the benefits of a smaller force coefficient. For our building, so the B is 25 and D is 25. So D is because we have L shape. According to our code, figure 4.4E. So for L-shape building, the effect building depth is the average between D1 and D2. So this is calculated as 25. So then HE over D is about 1.76. Our building is 90. So if we use the original 90, so it will be 3 to 4, but now it's only 1.76. And B over D is equal to 1. So if you look at the figure, so between 1 and 2, so the calculated force coefficient is 1.17. So that's the calculated force coefficient. And then the next step is size and dynamic factor. So for calculating the size and dynamic factor, so we need to follow the following step. So the first of all, we need to calculate the size factor. So that is in equation C1.18. So within this, we need to identify the half parameter length. That's the building breadth. So then we calculated that the size factor is a 0.97. Based on the size factor, bring in the size factor into equation 5.1 together with the geometry information, the height, the breadth, the natural frequency, and the damping ratio. We can calculate the size and dynamic factor at the top of the building. That is a 1.04. So then further, following the equation 5.2, we can calculate the size and dynamic factor along the whole elevation. So that is given in this column of the spreadsheet. So with all those information ready, we have the reference wind pressure, we have force coefficient, size, and dynamic factor. Then by using the spreadsheet, we can calculate distributed wind load along the building. And we can also calculate the shear force and the overturning moment. So the overturning moment we need to bear in mind because later we need to see whether we need to do any scale up by comparing with a crosswind based moment. So this is the calculation of the along wind force. Torsional force. So as introduced before, within this code, we give a new formula for calculating the torsional force, and this is a very simple formula. So the torsional load is provided as equivalent torsion. So the equivalent torsion is generated by shifted lateral force from the geometric center with the eccentricity E. So then how big the eccentricity is determined, it depends on the geometric ratio, B over D ratio. So if the B over D ratio is equal to 1, so then it's a square close to a square shape, we have the smallest eccentricity. So that is a 5% of the building breadth. If the B over D ratio is quite big, for example, very wide, so the eccentricity is bigger, it's 20%. So anything in between, we do so the B over D ratio is 6, so then it is 20%. Anything in between, we do an interpolation. In this particular working example, for WX1 direction, the B over D is smaller than 1, so it's a 5%. So E1 is about 5%, it's around 1 meter. So in direction 2, it is 8%, so the eccentricity. So then the calculated is about 3.2 meters. So then by the lateral force, by the eccentricity, for all the 4 directions, we can calculate the 4 different torsions. So for the all 4 different orthogonal directions. So finally, the torsional force will be picked as the biggest among the 4. So that is the calculation of the torsional force. Next one is a crosswind consideration. For the crosswind, this is why this working example is introduced. So we need to make a judgment whether the crosswind is significant. Within the code, actually, if you look at the flow chart, there is a diamond. So there are 3 criteria. If the building is shorter than 100, if the biggest slackness ratio in the 2 orthogonal directions are smaller than 5, and if the natural frequency in both directions they are bigger than 0.5 Hz, so then we believe they are not a crosswind resonance significant. So then we can ignore the calculation of the crosswind load. So in our case, all 3 criteria are satisfied. So then we don't need to do the crosswind checking. Then we go to the last step of loading calculation. That's the load combination. For the load combination, because we don't, the crosswind significant checking shows the crosswind will not be significant. So what we need to do is we use the lateral force from both orthogonal directions, that's from the along wind force, together with the torsional force to do a load combination. So the load combination factor is provided in table 2.1 in the COP. So we just follow the load combination factor, that's all. And regarding the serviceability, there is equation 2.4. So that provides a codified acceleration formula. That's related to the peak factor, the natural frequency, the damping ratio, the geometry information, and the mass. For the mass, we assume it is a 300 kg per meter square. So for the 1 year's return acceleration following this formula, we calculate it is about 0.024 meter per second square. So that is about 2.4 milli-G. So in the code, we also provide acceptable criteria. That is in figure 2.6. This acceptable criteria is a frequency dependence. We bring in our frequency, so it's about 0.5 hertz. So we can see, so the acceptable criteria, even for the most stringent one, is about 5. So here we are only about 2 point something milli-G. So we can pass the acceleration check. So there's no problem regarding the human comfort. So that's all for the structure wind load calculation. The next is for the cladding. So cladding one is a relatively straightforward. So first of all, what we need to do is we need to follow equation 2.3a. That's reference wind pressure, pressure coefficient, and size factor. The reference wind pressure, still we need to follow directionality, sheltering effects. That has all been calculated, so we don't repeat again. But one thing we need to bear in mind, as Alexis has introduced in the part 1, so new feature for the new code is the reference height for all through the elevation. It is top of the building. So then we have only one reference wind pressure, that is 2.13 kilopascal. Then we need to refer to figure 4.6a. That's give the zone key definition. So where is the edge? Where is the general? Where is the corner? So then, by looking at table B1.1, we know the net pressure coefficient for different zone keys, and also following appendix C1 for the size factor formula. So for suction, for edge zone, we can calculate size factor as a 1.22. So here I also need to remind, size factor is tubular area dependent. So then we assume the glass panel is 1 meter by 1 meter. So then we calculate for edge zone, the size factor is a 1.22. For other zone or general zone, it is a 1.96. And finally, bring in the reference wind pressure, the net pressure coefficient, and the size factor. We can calculate the positive and suctions at different zones of the building surface. And one thing I want to remind is, so here, within the code, it also has a clause in the notice. It says if sheltering effect is considered, cladding pressure within 50% of half of the displacement height, we can have a further 20% wind pressure reduction. So that's why within 0.5% of displacement height, that is about a 15.75 meters. So we can have a further 20% design pressure reduction. So that is all for the first working example. So then we go to the second working example. For the second working example, we introduce a further taller building. This is a tower with a 195 meters tall. The plan shape is a rectangular shape. So the dimension is B is 62.5, and the depth is about 39. And the natural frequency is actually calculated. It's about 0.25 hertz in the longer direction and 0.2 hertz in the natural direction. The objective of the case study is, so we also want to cover several unique features through this working example. The first one is, you can see, actually we have recessed corners. So we want to use this example to demonstrate when we consider the recessed corner. So with a corner modification, how the force coefficient can be calculated. The second one is because the tower is very tall, so definitely it is expected to be a crosswind significant. So then how to calculate the crosswind load? And further, if a crosswind base moment is bigger than a long wind, how a scaling up should be conducted? And the last one is, although we passed the initial check that our building can be used for codified approach, does that deem to be codified applicable? Is there any chance that in a later stage or suddenly realize, oh, maybe we still need to do a wind tunnel test? So we want to use this example to demonstrate we also need to conduct a further check regarding the need for wind tunnel testing. So again, the first step is initial judgment for standard approach applicability. So the same procedure, we don't get into details. So everything is fine. So the conclusion is the initial check shows we can use the standard approach to do the calculation. Then determination of a design wind pressure and the procedure are also the same. So first of all, we align our building and then we identify the directionality for 8 key directions, then radar plot. Then for each 90 degree, we pick up the biggest from the radar plot. Then the next one is so calculation of a reference wind pressure. So we have some assumptions here. So first of all, we assume the building is in a very open exposure. So then there's no sheltering effect. So you can see, so in the last example, the ZE is significantly smaller than Z, but here we can see the no sheltering effect. So the ZE is equal to Z. And second, we consider it is on a flat terrain, so topography factor is equal to 1. So then very straightforward by using the QZ flat directionality and the topographic factor. So we can calculate the reference wind pressure. Next one is calculation of a long wind force. So here, similar to before, we need to identify the H over D and B over D ratio. For this project, H over D is 5, B over D is 1.61. So if we look at H over D is 5, so that will be the orange curve. And B over D is 1.6, so we can identify the force coefficient is 1.37. As I said, we want to use this case to demonstrate the corner of the modification. So we want to remind the user, for this case, actually, we have a recessed corner. The recessed corner dimension is about 3 meters. So then we need to refer to equation 4.2 within our code, the COP. The COP here, the W is the recessed corner dimension. So by bringing in the 3 meters, bring in the 3 meters in and bring in the total building breadth, so we can calculate the factor is 0.97. So we can have a 3% reduction on the force coefficient. Then the final force coefficient is the product between the two. So that is a 1.33. So that's the final force coefficient we are going to use. After the force coefficient calculation, we need to calculate the size and dynamic factor. The first step is we need to list out all the needed parameters, the geometry information, natural frequency, and the damping ratio. So very important, as introduced in the first part, the damping ratio in 2004 wind code is constant. So normally it's recommended as 2% for RC and 1.5% for the steel. So for our case, actually in the 2019, it depends on the slenderness ratio. So later we can see that for 2 different directions, table C2/1 to calculate the damping ratio. So then the other formula will be the same as introduced in the first working example. We calculate the size factor by using building breadth. And then we calculate the size and dynamic factor at the top of the building. And then by using this formula, we calculate the distributed size and dynamic factor along the building elevation. So we can see the trend is on the top of the building, the size and dynamic factor is the biggest. And at the bottom, it gradually reduced. At the bottom is the smallest. And then we calculate the distributed wind force at different levels, and we can calculate the along wind overturning moment at the bottom. So for this direction, minus Wx2, so that will be 3,569 meganewton. The next is the torsional force calculation. The torsional force calculation will be the same as what you introduced in the previous working example. So we know the B over D ratio. We identify the eccentricity in the two directions. And then we calculate the torsional force in the two orthogonal directions. And the final torsional load will be picked up as the biggest one between the two. So next is a crosswind calculation. So this is the key point. The reason why we want to introduce this working example. Still, within this diamond box, we need to make a judgment whether the crosswind is significant or not. So list all the criteria. So the first one is whether the building is taller than 100. So our building is 195. So very obviously, we cannot fulfill this requirement. So that means the crosswind response can be significant in this case, so that we cannot get rid of a crosswind base moment calculation. Then what we need to do next is we use the code provided a crosswind base moment formula. So that is within equation 2.2. Within this, because the crosswind is a purely dynamic effect, so it relate to several parameters, including the building geometry, including the reference wind pressure on the top of the building, and then here it is turbulence intensity and peak factor. So after this, it is actually the mean velocity at the top of the building. As I said, it is a dynamic. It's a purely resonant effect, so it's highly sensitive to the natural frequency and the damping ratio. So bring in all those factors parameters into equation 2.2. So the natural frequency, using the natural frequency, we can calculate the peak factor. So that is a 3.5. So one thing we want to highlight is here the natural frequency is the vibration direction or the loading direction. So it's not an approaching wind direction, it's actual loading direction. So that's why we call it NY. So that means if we talk about the load as a crosswind, so the natural frequency should also be in the crosswind direction. So that's NY to calculate the peak factor. So then the gamma W, that's the load factor, partial load factor too. So in Hong Kong for wind, we normally use 1.4. And natural frequency and turbulence intensity. Then the damping ratio. So with all those parameters bring in, we can calculate the crosswind base moment in the Wx2 plus direction will be 1,759 meganewton meter. So then if we repeat the same procedure for all the directions, all the 4 orthogonal directions. So we can see for all the 4 orthogonal directions, we can have a 4 along wind base moment. We can also have a 4 crosswind base moment. And for the along wind base moment is a single direction, because you can see in this figure, the black arrow means the approaching wind direction. So the orange arrow means the long wind loading direction. So you can see for the long wind, it's only one direction. It's in the same direction as the approaching wind. But for a crosswind, the blue arrow is a plus and minus because it's purely resonant effect. It can be both plus and minus. So what we need to do is we need to check whether a crosswind is bigger or smaller than a long wind effect. So then we can make a further judgment whether we need to do any further action. So one thing we must bear in mind is, although in part 1, Alexis has introduced to say, we need to compare the ratio between the long wind moment and the crosswind base moment. But we need to bear in mind this ratio is the load in the same loading direction, not the wind approaching direction. For example, here, what we need to compare is, for example, for the vertical direction as the arrow shows. So then what we need to pick up is the two blue arrows, the crosswind. So that is 2432 and 2581. So in the vertical direction. And we need to compare against the long wind in the same loading direction. So that will be 3.3569 and 3.69. So then we pick up the bigger one between the crosswind. We pick up the bigger one between the long wind. The ratio is 0.7. So for the vertical direction, the crosswind is smaller than the long wind. It's smaller than 1.5, smaller than 1.5. And for the horizontal direction, following the same strategy, so we pick up the crosswind, so 1759, and a long wind in the same direction, so that's 1757 and 1821. So the ratio between the two is a 0.97, also smaller than 1.5. So it means we don't need to do the wind tunnel test, because if any of the two values that is bigger than 1.5, we need to do the wind tunnel test. But now we are satisfactory. But still, we need to check whether for all the 4 directions, the long wind are all bigger than the crosswind. So it seems for the horizontal direction, there may be a chance that because it's 0.97 is quite close to 1, there may be a chance that the a crosswind is bigger. So we double check. So we pick up the smaller long wind. So that is 1757. So still it's very close to 1. So still, although it is the crosswind is slightly bigger, but very close to 1. So we think that's okay. We don't need to do the further adjustment. So for this scenario, we say we don't need to do any further action because the long wind base moment is equal to or bigger than the crosswind base moment. So we can use the long wind in the 2 orthogonal direction to do the load count directly. So that's first scenario. And the second scenario, we change the parameter a little bit. So what we do the revision is originally for x1 direction, we assume the natural frequency is a 0.25 Hertz. So this time we reduce the natural frequency in the x1 direction to 0.21. So then we recalculate all the long wind and the crosswind. So especially the crosswind, it is very sensitive in this direction to the natural frequency. So as what is highlighted in red, so in this direction, because we reduce the natural frequency, so it is increased from the previous 1759 into the 2175. So that is increased. So let's do the comparison again. So for the vertical direction, there's no change because we don't make any further adjustment. For the horizontal direction, because we have increased the crosswind base moment. So then this time, in this direction, the crosswind is bigger than the long wind. So the ratio is 1.16. But still, it is smaller than 1.5. So that means it's okay. We don't need to do the wind tunnel test. However, if we see in this direction, the horizontal direction, the crosswind has already been bigger than the along wind. The ratio between the two is 1.16 and 1.21. So we need to use these two as a scaling factor to multiply or scale up the distributed along wind force in those two directions to make sure the finally adopted design wind load can cover the crosswind base moment effect. So this is the along wind force need to be scaled up. So this is the second scenario. And third scenario is we further reduce the natural frequency in the x1 direction. We reduce it into 0.15. So in this case, the crosswind base moment is increased substantially. So that is increased to 3272. So again, let's check for the horizontal direction. So now this time, if we pick up the biggest value between the crosswind and along wind, the ratio becomes 1.6. So exceeding 1.5. So then according to the code, if the crosswind base moment is larger than 50% than the along wind base moment, then the codified approach doesn't apply anymore, and a wind tunnel test approach will become compulsory. So then need to do the wind tunnel test. So that means, so through this working example, actually in the exercise, so even we pass the initial checking, it doesn't imply it's 100%. There's no chance to do the wind tunnel test. So still, in a later stage, after we have calculated both the long wind base moment and the crosswind base moment, we need to do a further checking. Yeah, this is also a very key character want to be demonstrated through this working example. And then finally, we go to the load combination. So what we need to use is the along wind force and also the scaled up to the along wind force. So to make sure that the adopted design wind force will not be smaller than the crosswind base moment. So the scale up to along wind force and the torsional moment to do the load combination following the load combination table in the code. And finally, it's the human comfort check. For the human comfort check, similar to as before, we bring in all the parameters. And for the 1 year acceleration, we are about 0.25 Hertz. So the threshold, the criteria is about 6 or 7 milli-G. But our calculated acceleration is only about 3 to 3.5 milli-G. So again, we pass the human comfort checking. So there's no problem for the human comfort for this actual example. And then it's the cladding pressure. So for the cladding pressure, this time we assume a panel size of 2.5 meters by 2.5 meter. So the half perimeter length is 5 meter. And the procedure will be exactly the same as what we introduced before. So we follow the figure 4.5a to identify the zone key. So then for different zones, based on the the panel size, we can calculate the size factor. And also for different zones, but referring to table B1.1, we can get the net pressure coefficient. And finally, the reference wind pressure is the top of the building, that's QH. And then but multiply all those positive wind pressure and the negative wind pressure. So that will be the calculation of the cladding wind pressure. And this time, because there's no displacement height and no sheltering effect, so everywhere the cladding pressure are the same, all through the elevation, but the corner and the general zones, they are different. So that's all for the working example presentation today. And later we will have 15 minutes break. And so don't walk away. Welcome you to be back. And we have a Q&A section after the 15 minutes break. And welcome, you can share with us with all your questions or queries. Yep, thank you. See you later.